In this video, we're going to discuss term-by-term integration of power series, which we'll see is almost identical to term-by-term differentiation. Suppose we have a function f of x and a power series representation for that function given by the sum from n equals 0 to infinity of c sub n x to the n. We would like to know if we could find a power series representation for some antiderivative capital F of x of this function f of x using the power series representation that we're given for f. We can proceed just as in the case of term-by-term differentiation by thinking of our power series as a polynomial that has infinitely many terms and simply integrating term by term. If we did that in this case, we would see that the constant term c sub 0 would have an antiderivative of c sub 0 times x. The linear term, the first degree term, c1 times x, would have an antiderivative of c1 x squared all over 2. Our third term, c2 x squared, would antidifferentiate to c2 x cubed over 3. And of course, we could continue on with as many terms as we'd want. And we also have to remember that since we're antidifferentiating, we do need to have an arbitrary constant, which we'll just add in the front where a constant would go in a power series, and we'll just call that constant c as we would in any other sort of integral situation. We could then also do the same thing with our general term, c sub n x to the n, and so we'll have our series n equals 0 to infinity of c to the n x to the n plus 1 all over n plus 1. So here we're using the antiderivative via the power rule of x to the n as x to the n plus 1 over n plus 1. Now notice we also need to include a plus c here, and so we can make room for that and just add an arbitrary constant up front for our arbitrary constant of integration. Again, this is intuitive and works for polynomials, and our hope would be that the same reasoning and logic works for power series, and just like was the case with derivatives, this works as well for power series. The formal statement of this is often called the term-by-term integration theorem, and it says that if we have a function f of x and a power series representation centered at a for that function given by the sum n equals 0 to infinity of c sub n times x minus a to the n on an interval a minus r to a plus r, then the antiderivative of f of x, or indefinite integral of f of x dx, can also be represented as a power series on that same interval from a minus r to a plus r, and the integral of f of x dx is given by the arbitrary constant c plus the sum from n equals 0 to infinity of c sub n x minus a to the n plus 1 all over n plus 1. This is obtained by taking the general term for the power series for f and antidifferentiating it to give us the formula Cn x minus a to the n plus 1 all over n plus 1. In this example, we want to find a power series representation for the function f of x equals the natural log of 1 plus x. If we think about the natural log of 1 plus x, we might realize that this is an antiderivative of the function 1 over 1 plus x. And of course, 1 over 1 plus x we can write as 1 minus negative x. We can find a power series representation for 1 over 1 minus x squared by manipulating the geometric series function, and therefore use term-by-term integration to find a power series representation for the function that we want, the natural log of 1 plus x. So we start with our function 1 over 1 minus negative x, and we write this as a power series using the geometric sum formula as n equals 0 to infinity of negative x to the nth power. We can then break this up so that we have the series from n equals 0 to infinity of negative 1 to the n times x to the n. Now notice that the negative 1 to the n part of this series is actually just a constant. Even though it involves n, it does not involve x, and therefore it's always either positive or negative 1 depending on what term in this series we're considering. If we want to write out the first several terms of this series, we can do that quite easily. They would be 1 minus x plus x squared minus x cubed, and so on. Now that we have our power series representation for 1 over 1 minus negative x, we're able to find one for natural log of 1 plus x using term-by-term integration. We'll first look at the compact sigma notation for our power series representation of 1 over 1 minus negative x, which is n equals 0 to infinity of negative 1 to the n times x to the n. To antidifferentiate this, we're going to take our arbitrary constant c and then take our series from n equals 0 to infinity of the antiderivative of our term formula, negative 1 to the n times x to the n. Negative 1 to the n is a constant, so nothing happens there, just stays as negative 1 to the n. And then we have x to the n plus 1 divided by n plus 1. And this gives us a formula for our power series representation of natural log of 1 plus x, an arbitrary constant c, which we'll have to determine in a moment, plus the sum from n equals 0 to infinity of negative 1 to the n, x to the n plus 1 over n plus 1. If we write out the first several terms, we can integrate each of the terms of our original power series, and we will obtain c, arbitrary constant c, plus x, minus x squared over 2, plus x cubed over 3, minus x to the 4th over 4, etc. The last step here is we do need to figure out the value of our constant c. Since we don't have an arbitrary antiderivative, we want the very specific antiderivative of natural log of 1 plus x. In order to do this, we can simply substitute some value in for x on both sides of the equation and then solve for c. In this case, an easy value to check would be x equal to 0. And the reason that we can pick that is because when I substitute x equal to 0 into the natural log of 1 plus x, we get the natural log of 1 plus 0, which is the natural log of 1. When I substitute x equal to 0 into our expanded out series, we're going to get c plus 0, minus 0, plus 0, minus 0, and so on. We know that every term that involves some power of x will be 0. And so what we get here is simply that natural log of 1, which is equal to 0, is equal to c. And so we must have 0 equal to c here. And therefore, the power series that we're looking for, that represents natural log of 1 plus x, is going to equal the sum from n equals 0 to infinity of negative 1 to the n times x to the n plus 1 all over n plus 1. There's no arbitrary constant c here, since we found that c is equal to 0 when we have the natural log of 1 plus x as our specific antiderivative. If you'd like to try a similar example, you can pause the video and find a power series representation for the function f of x equals the arctangent of x. If you need a hint, consider differentiating the arctangent of x so that you could write the arctangent as an antiderivative of a function. Resume the video and see the full solution in a few seconds. We know the derivative of the arctangent function is 1 over 1 plus x squared, and therefore the arctangent of x can be thought of as the antiderivative of 1 over 1 plus x squared, which we can write as 1 over 1 minus negative x squared. So we start by finding a power series representation for 1 over 1 minus negative x squared, and then antidifferentiate it term by term. 1 over 1 minus negative x squared is a geometric series where negative x squared is substituted in for x, and therefore the power series representation is the sum from n equals 0 to infinity of negative x squared quantity to the n, which we can write as the sum from n equal to 0 to infinity of negative 1 to the n times x to the 2n. The first several terms of this series, if we wrote it out as an expanded form, would be 1 minus x squared plus x to the 4th minus x to the 6th, etc. We then integrate this term by term, so that the arctangent of x is our arbitrary constant c, which we will find a specific value for in a moment, plus the sum from n equals 0 to infinity of the constant negative 1 to the n times x to the 2n plus 1 over 2n plus 1. Here we're anti-differentiating x to the 2n using the power rule by adding 1 to the exponent to get x to the 2n plus 1, and then dividing by this new exponent, 2n plus 1. If we apply this to each of the first several terms of our series, we see that we get c, the arbitrary constant, plus x minus x cubed over 3, plus x to the 5th over 5, minus x to the 7th over 7, etc. And our last step is to find the specific value of c that gives us the arctangent function, arctangent x. If we substitute x equals 0 into our function and our series, we get that the arctangent of 0 is going to equal c plus 0 minus 0, etc. And so the arctangent of 0 is equal to c. Since the arctangent of 0 is equal to 0, we get that c is equal to 0, and therefore the power series representation for arctangent of x is the power series that we found in above without the arbitrary constant c. So the series from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1, all divided by 2n plus 1, with first terms x minus x cubed over 3, plus x to the 5th over 5, minus x to the 7th over 7, and so on.